Okay, now we're ready for the second part, or to finish up this sequences worksheet. We're going to look at examples 5, 6, and 7. So example 5 is pretty interesting. It says, determine if this sequence will converge, diverge, and if it converges, find the limit. So we have some interesting things going on here. We have this in factorial. And so if you recall, or if you've never seen it before, in factorial is equal to n, or I should start with 1, I'll start with 1. 1 times 2 times 3 times 4 times n minus 1 times n. So for instance, 4 factorial would equal to 1 times 2 times 3 times 4. That is what factorial means. Okay, so we see we have this. Now to decide what's happening with this one, we notice that it's got this alternating thing going on, right? We still have that negative right there. It means it's alternating. So we want to consider the absolute value of, let's look at the limit as n goes to infinity of the absolute value of a sub n. Let's look at that guy. So that is going to be, what that does basically is knock off the negative. So this becomes 4 to the n over n factorial. So what we can do here is write out a few terms. That's going to help us reason through this one because it's not as simple as a L'Hopital rule or something like that. So let's write out a few terms. So when n is 1, what we get here is 4 to the 1 over 1 factorial, right? And then when n is 2, we get the second term would be 4 to the 2 over 2 factorial. And the third term would be 4 to the 3 over 3 factorial. And so if we look for very large values of n, what do we have? Let's write a sub n, okay? A sub n is going to be 4 times 4 is 4 to the n. So 4 times 4 times 4 times 4, a bunch of 4s, n times n of these guys, right? Okay, then what is in the denominator? Well, the denominator is going to be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, and way down here is going to be times n minus 1 times n. That's what we're going to have here, okay? So let's just consider what's going on here. Right here we have 4 over 1, okay? 4 over 2, 4 over 3. So right here we have 4 times 4 times 4, which is 4 cubed, over 1 times 2 times 3, which is 6. We have this. And then we have this middle part here. Let's look at what's happening in this middle part. Well, in this middle part we have 4 over 4, which is a 1. So these are being multiplied, right? So times 1 wouldn't change that value, okay? And then then we'd have 4 over 5, right? 4 over 6, but 4 over 5 is less than 1. This is something that's less than 1. And 4 over 6 is less than 1. And so this is less than 1, this is less than 1, this is less than 1. 4 over n minus 1 is also less than 1. So we have this value times some stuff that's less than 1. When you take a number and you multiply it times some things less than 1, it's going to be smaller, right? If you take the number, let's take 8. If we multiply 8 by something bigger than 1, it's going to get bigger. If we multiply it by something smaller than 1, let's say 4/5, or maybe 3/4, that'd be easier one to see, 3/4, what happens to our value? Well, 4 goes into 8 2 times 3, it becomes 6. So when you multiply 8 by something less than 1, it gets smaller. When you multiply any value by something less than 1, it gets smaller. Okay, that's important for us to take note of. So what we're going to do kind of here is the squeeze theorem. So what we have here is we can say, well, look at these values here, okay? 4 cubed over 6 is definitely, it's bigger than 0, right? So I can say 0 is less than, we say less than or equal to, it's fine. A sub n, this whole term is a sub n, right? A sub n. But this is going to be less than or equal to the biggest value that we can have here. And the biggest value we can have here would be, let's multiply this times this last value there. It'd be 4 cubed, because all of this stuff's less than 1. 4 cubed times 4 over 6n. Okay? A sub n is going to be bigger than 0, and it's going to be less than or equal to this guy right here. So this, if you recall the squeeze theorem from Calc 1, where we were trying to find the limit of a function and we squeezed it between two others, we're doing something similar here. Let's take the limit as x goes to 0 of 0, and that's 0. And let's convert this to function notation. The limit as x goes to, I'm not 0, I meant infinity. Doesn't matter what x is going to of 0, it's going to be 0. As x goes to infinity of 4 to the 4th, which is 256. Is that right? No, let me measure. I think that's right. 64 times 4 is 16. Yeah, 256, okay, over 6x. Okay. Well, that x in the denominator is going to get so big, this is going to go to 0. So what we find is the limiting value on the outside as x goes to infinity is 0. The limiting value on the right side as x gets large is infinity, and this is between those two. So the limit as x goes to infinity of a sub n, or if we turn in terms of x, it's going to be also 0. Maybe I'll call it n of a sub n. Is also 0 by the squeeze theorem. I guess in this example I should have left these in n's because it sort of makes more sense. But it would be 0. We got squeezed to figure out that the limit is 0. All right, what did that tell us? Well, this was the absolute value, right? So we said if the limit as n goes to infinity of the absolute value of n is 0, then the sequence a sub n converges to 0. So this was a good example. We had to reason through some stuff, and we remembered what factorial was, which will be a good thing for us to know what that is. Okay, cool. Now we have a rule, which I think this should look kind of familiar for sequences, because I know why it should look familiar is because when you were in pre-calc, you saw some of this for series, which is coming next, but we're in sequences, which is the list of numbers, okay? It says, if you've got a sequence that's defined as a sub n is equal to r to a power n, if that value r that you are raising to a power is between -1 and 1, and even equal to 1, then this sequence will converge. If that value r is between -1 and 1, it will converge to 0. And if r is equal to 1, it will converge to 1. So that's what this rule says. So because of that rule, that makes example 6 pretty straightforward. Let's look at example 6 right here. And so the first one says a sub n is equal to 30 to the n. All right? Well, this looks a lot like r to the n, right? So what would be the value of r right there? In the first example, the value of r is just a 3. So let's see what that looks like. Determine whether the sequence converges or diverges. If it converges, find the limit. So this is example 6. The first one says a sub n is 3 to the n. Well, this totally looks like r to the n to me. So r is equal to 3. Well, 3 is not in between. This is the rule. If r is between -1 and 1, it's going to converge to 0. A sub n will converge to 0. And if r is equal to 1, it will converge to 1. Else, if r is not in between those values, it diverges. Well, r is 3. That's not in between these values, and so it's going to diverge. All right, so let's look at B. For B, we have a sub n is equal to 0.3 to the n. 0.3 can be thought of as 3 over 10. Well, this is r to the n, so 3/10 is definitely in between -1 and 1, so this will converge to 0, just like that. All right, so that's kind of nice. Let's look at C. All right, we've got a sub n is equal to -1.4 to the n. All right, well, that negative, let's pull it out. -1 to the n, 1.4 to the n. Okay, this is positive, negative, that's what that's doing. Okay, we can say, well, what's the limit as n goes to infinity of a sub n? Let's see what that's going to look like. Okay, well, the limit as n goes to infinity of a sub n would be where we knock that part off. So we're considering just 1.4 to the n, right? But this is an r to the n sequence. And so we know if r is not between -1 and 1, and it's not, that this will diverge. So it's going to, the absolute value of a sub n will diverge, so a sub n was going to diverge. This will diverge. Okay, a sub n is equal to D, the last one here. A sub n is equal to -2/3 to the nth power. All right. This is also alternating, so let's consider the absolute value of a sub n. That types out the negative, so we're looking at basically 2/3 to the n. All right. R is 2/3. It's between 0 and 1, so that means that the limit as n goes to infinity of a sub n is 0 because it converges to 0, and so that means that a sub n converges to 0. So this little rule is handy when we have something being raised to a power. All right, cool. Last example. Let's see what this is. Oh, before we get to the last example, we have new definitions. So they go like this. A sequence is called increasing if a sub n is less than a sub n plus 1 for all n greater than 1. So what that means basically is the sequence increases if as you move up your list, a sub 1, a sub 2, a sub 3, the values are increasing always bigger than the one before it. That's what that means. Similarly, a sequence is called decreasing if a sub n is greater than a sub n plus 1 for all n greater than or equal to 1. That means in our list of numbers, it's decreasing if the next value is smaller, smaller, smaller. They're always getting smaller than the term before. Okay. If you have a sequence that is either increasing or decreasing, it gets a name called monotonic. That's its name. We can say a sequence is bounded. It can be bounded above if there's a number m such that the a sub n is less than that value. The biggest number on your list is less than a sub n. I mean, it's less than m. It can be bounded below if you can find a lower number for which your values are either less than or equal to that number. So it can be bounded above or below. If it's bounded above and below, both of those, it's called a bounded sequence. All right, let's use some of these words in an example. Example 7 goes like this. Is the sequence increasing, decreasing, or not monotonic? And is it bounded? Okay, so let's see what we can say about these guys. Here we go. A sub n is 1/4 to the n. Let's talk about this guy. The question is this increasing, decreasing, or not monotonic? Okay, I'm going to use a little calculus to help us out here. Let's consider the function. F of x is, and you can see that this is really 1/4 to the x. I mean, 1/4 to the n, I'm sorry. The n. That's the same thing. So I'm going to consider the function f of x is 1/4 to the x. All right. I want to know if this is increasing or decreasing. That's what I'd like to know. So we can consider this function. Let's take a derivative here. F prime of x is, this is change. This is, if you had e to the x, the rule is it's just e to the x, right? But this is not the base e. So what we do is we still say it's 1/4 to the x as its derivative, 1/4 to the x, times the natural log of the base that's being raised, times the natural log of 4. All right. Well, the natural log of 4, if you put that in your calculator or if you look at a graph, it's going to be a negative value. So this is a negative value. All right. And then if you have a base to a power, it doesn't matter what the base is. If it's being raised to a power, if you look at the graph, this is always positive. Well, what we have here is a positive times a negative, which is a negative. So what we see here is that the derivative is going to be negative for every value of x right here. That's in the domain, right? Or no, every value. So it's always negative. What does that mean about the function f? What that means about the function f is that f is always decreasing. So that means that this sequence is decreasing. All right, that is that part. Now, is it bounded? Well, let's put out some terms here and see what we get here, right? A sub 1 would be 1/4. A sub 2 would be 1/16. A sub 3 would be 1/4 cubed, which is 64. So we know it's always getting smaller. So we know this is the biggest number. So we can say this. A sub n will always be either less than or equal to 1/4. All these other terms are going to be less than that, right? But these are always positive. We're never going to get to 0. So this is a bounded. Yes, it's bounded. It's always decreasing, and it's a bounded sequence. And this is what it's bounded by. All right, B. A sub n is 3n minus 1 all over 2n plus 2. Okay, is it increasing, decreasing? Is it bounded? So let's see what we can do with that. Hang on just one second. I have to pause something.